Ms. Diaz. It's a great pleasure for me to be here at Lima. This is my first visit here. I'd like to thank Dr. Daxa. I'd like to thank Carlos, who made it possible for us to come and speak with you today. And I have to tell you that I very much enjoy the weather and the food here in comparison to what's happening at home. So today I thought I'd talk to you about some of our work. We spend a lot of time trying to characterize the molecular pathogenesis of lymphomas in general. And I will speak principally today about mass spectrometry as a platform for discovery. And you'll find in my presentation that it requires a collaborative approach. So I usually put a slide here just to talk about the disclosure. Can everybody hear me? Okay, I thought I lost transmission. For a company co-founded while I was in Ann Arbor, Michigan, but it has little relevance to what we're going to be talking about today. So by way of outline, we're going to review the interest of our laboratory and the paradigm that we use. And please consider this a discussion rather than a seminar. So if you have any questions, please feel free to ask. I've got the headset on, and I can always listen to the interpretation. I'll talk to you about proteomics and mass spectrometry. I'll talk to you about how we use that to identify oncogenic and targetable pathways in T-cell neoplasia, and I'll offer some conclusions and some implications. So we think of precision medicine as an integrated platform that requires studying using model systems, and perhaps the most important part of it really is to have tissues that people will use to study human diseases. You can create as many mouse models as you want, but unless the biology is driven by tissue-based analyses, you're going to be coming up with findings that are not as relevant to the human diseases. We use a lot of high-dimensional tools. So we use next-generation sequencing for unbiased interrogation of the samples. And that way, you don't have to make any assumptions as to what you're going to find. As a matter of fact, it is a hypothesis-generating approach rather than a hypothesis-driven approach. And we've given up on basically building hypotheses as opposed to generating hypotheses using high-dimensional approaches. Okay. So a laboratory pretty much studies exclusively lymphomas of all kinds. We're biased to using as you can see here, the central dogma. So we interrogate DNA high-dimensionally, do the same thing with RNA and proteins by mass spectrometry. We do some functional studies, which include some functional screens. We have a big interest in proteolysis, but more importantly, all of these are mechanistic studies, end up being modeled in the animal, but we always have to go back to the patient to make it relevant. So I'll take the opportunity to talk to you about proteomics and mass spectrometry. So everybody knows that the genome, the human genome, encodes about 23 to 26,000 coding genes is the estimate based on the sequencing of the human genome. And that's responsible for encoding about over 1 million proteins if you include isoforms and post-translational modifications. Now, interrogating proteins in comparison to DNA, for example, is a lot more complicated. It's complicated because of two main problems, which are complexity, like I've expressed in my first slide here, 1 million different proteins out of 26,000 genes, and the dynamic range. So you have proteins such as albumin, which are present at milligram per microliter quantities in milligram per mil quantities in like serum, for example, and in whole blood. And then you have cytokines which are located in the femtomolar region. So that dynamic range, about 7 orders of magnitude, is very hard to interrogate from one platform. So I told you there's massive complexity, and I told you there's massive dynamic range, very difficult to interrogate from one platform. In any event, we use mass spectrometry for unbiased discovery projects in proteomics. And so proteomics is the equivalent of genomics and involves the entire protein complement encoded by a tissue, an organ, or an organism for that matter. So credit for mass spectrometry goes to John Joseph Thomson, who worked out in the Cavendish Laboratory at Cambridge. He was the one who first identified isotopes. And he got his technical assistant at that time, Francis, asked him to build the first mass spectrometer. Now, both of these individuals won Nobel Prizes for their work, and John Joseph Thomson is one of 2 people who won a Nobel Prize, and 7 of his students got to win Nobel Prizes. So, no pressure, Carlos. So mass spec-driven proteomics, like I mentioned, proteomics is the large-scale study of the proteome. And mass spectrometry, the unambiguous identify protein, that means you can identify protein without any question, right? This is in comparison to antibody-driven approaches where you have to trust that the antibody itself recognizes the protein of interest. And we know very frequently that antibodies may recognize more than one protein. It's unbiased, and it can identify the precise site of the post-translational modification. There are hundreds of these post-translational modifications. Phosphorylation is an example, ubiquiration is an example, methylation. All of these can happen in proteins, and they can occur at several different sites in the same protein. And they're very important in how the protein behaves and how it controls the biology of the cell. For example, phosphorylation regulated by kinases or phosphatases are very important in cancer pathogenesis. If you overexpress a tyrosine kinase, you can drive oncogenesis. And that's a very common paradigm. Also, if you delete a phosphatase, you can remove the negative regulation and again lead to overactivity of the kinase. So we use this simple paradigm here for mass spectrometry-driven work. There are 4 principal stages. The first stage is pre-analytical simplification. We do bottom-up proteomics using a series of enzymes. Our favorite enzyme is trypsin because it predictably cleaves between lysins, carboxyl to lysins and arginines. The platform on which we run our digestive peptides is electrospray tandem mass spectrometry, which we do exclusively in our laboratory. And like everything else hydrometrically these days, you need to do some bioinformatic analysis. So every mass spectrometer has 3 components, right? It has an ionization source, it has a mass analyzer, it has a detector. And so the mass spectrometers are known by the name of the ionization source and the mass analyzer. So the example I offer here is MALDI-TAR, which is matrix-assisted laser diesel to ionization time of flight. And I'll show you what that is. So what you do is that you fire a laser onto your tissues or the proteins that have been digested into peptides and bonded to what's known as a target. And then the small protein peptide, the small peptides now travel to the detector, and the larger ones take a longer period to get there and in a fixed distance. So the larger peptides get to the detector later, and you can reverse calculate what the mass to charge of that particle is. The method that we use virtually exclusively in our lab also won the Nobel Prize just like the other one. This was won by John Fenn in 2002. This method is called electrospray and is reasonably different from the MALDI. So I'll illustrate that to you in this video. So what happens is that you apply a potential difference between the nozzle of the HPLC into the inlet of the mass spectrometer, and then when the particles enter the mass spectrometer, those particles are now naked charge. This potential difference boils off the solvents in the desulfation process. That gets into the mass spectrometer with these naked charges. These metallic rods here are octopoles, which basically concentrate the peptides in ion, what's called a coherent ion packet. Now, what I showed you in time of flight mass spectrometry was a linear flight path. Well, this is a more or less a circular ion path. So what that means is that it doesn't matter how close two particles are, they will be separated because I can run them indefinitely by running radio frequency voltages. And these are recorded as sine waves, and these sine waves are now used to collect information which is relevant to the tandem mass spectrum. So this is what the tandem mass spectrum of STAT3, a very common protein, looks like. And this slide I show exclusively to demonstrate that you only need two peptides to unequivocally identify a protein. So now that we can identify a protein, here's an example of a post-translational modification, which is phosphorylation. And phosphorylation leads to a 98 Dalton change in the mass of a particular peptide. In this example here, this is a phosphorylated serine, which is picked up by mass spectrometry. So we've devised a workflow. This is not unusual, but importantly, we can ask what the level of phosphorylation is in comparison to all of the proteins that are expressed in the cell. So we can do whole proteomics, which is the equivalent of doing 6,000 Western blots at once. And at the same time, you can interrogate phosphorylation at a specific residue. So when we do these experiments, so when Carlos was in the lab, we were able at best to interrogate a total whole proteome of maybe about 800 to 1,000 proteins, total proteins, and maybe about 5,000 phosphorylated proteins. Today, we can interrogate easily 6,000 proteins with a whole proteome and 17,000 phosphosites at once. So you can imagine how much data that is and how powerful that is if you were to just change one single parameter and see what happened globally to the cell in terms of the signal. So using this tool, that's basically what I just told you. You can interrogate in excess of 6,000 proteins and look at 17,000 peptides, phosphorylated peptides, and we can ask simple questions like, what happens if I inhibit my favorite kinase? Okay. So this is to show that this experiment is highly reproducible, very highly reproducible when we do multiple different approaches. And so these are Pearson correlation plots here that just show that multiple iterations just give us a high correlation in excess of 0.9. The R-squared values are in excess of 0.9. Okay. So Dr. Lim really likes studying out positive lymphomas, and she'll tell you a little bit about that in the presentation, I hope. I'll say a little bit as well. But we can ask specifically what happens when you inhibit ALK-driven tumors using the inhibitor crizotinib, and what residues that are phosphorylated are changed in comparison to the total protein and unmodified peptide. So using that approach, we're able to discover novel sites that are regulated by ALK. So if you inhibit ALK and you lose signal, then using a specific inhibitor, then you can surmise that that site is regulated by ALK itself. So this ALK 1604, Y1604 is the residue which is used by the commercially available antibody to represent ALK activity, right, Carlos? You've used that before. But what I'm showing you here is that there's multiple ALK sites. So when you inhibit using crizotinib, you can see a massive decrease in the phosphorylation at Y1604 relative to ALK expression for the unmodified peptide. And then there are some residues in which there is no change. But there are other residues in which you have just as big changes, but nobody's made a commercial antibody to them, making the assumption that this is the most important one, but that is not necessarily the case. With that in mind also, you can see some of the downstream signaling components of the ALK pathway here. So here are some stats. So this is stat 3Y705, which I'm sure Carlos is aware of, and SHIP, which is also downstream of ALK. And this is an unknown, well, I'll say it's known to us. I'm not telling you what it is. Protein and site that is regulated by ALK inhibition, which we can show is regulated by ALK, doing an experiment like this. So you can reconstruct the tyrosine kinase signaling of an oncogenic tyrosine kinase doing one of these kinds of experiments. And what it teaches you is new biology. It teaches you about how phosphosignaling engaged by a receptor tyrosine kinase can change parts of the cell that you wouldn't. There's no way, it doesn't matter how smart you are, to have figured out exactly what kind of biology is good, and more importantly, where exactly in the protein the regulation is occurring. So we can do that with high sensitivity. So Delphine Roland, when she was in the lab, decided to use this approach for the discovery of new oncogenic tyrosine kinases. And I'll show you an example of that. And we developed the concept of outlier kinase profiles during that period. So here is what happens when you do phosphosignaling experiments like I just showed you using an ALK-driven kinase, or an ALK-driven tumor. So let's say, for instance, this is anaplastic lymphoma kinase. Your recovery here basically shows that the largest number of phosphorylated tyrosine peptides go to this protein, and everything else is very small. You can depict that in one of these interquartile bar graphs, and you can see that this is ALK here, which is an outlier. The same thing happens if you look at ALK in non-small cell lung cancer, which is also driven by ALK. So the fusion here is ENL4 ALK. So ALK is an outlier, and the proteins that are located here are potential signaling targets. The same thing happens if you use a line in the like 562, which is driven by ABL, the BCR-ABL fusion in CMS. So ABL here is the oncogenic kinase. So using that strategy, we decided to interrogate some targetable pathways in T-cell replacement. So I will talk to you about these two entities boxed in here, which is part of the 2016 classification of T-cell replacement. So the first one here, the primary continuous CD30 positive lymphoproteinuric disorders, and the second is the ALK negative ALCS. Okay, so there are many pathologists in the audience, so you would know that primary continuous CD30 positive T-cell lymphoproteinuric disorders. The second most common form of T-cell lymphomas, they are represented by two types: lymphomatoid papulosis and primary continuous anaplastic large cell lymphoma. These are united by the fact that they show strong reactivity for CD30 and consistent genetic abnormalities that were targetable hadn't been described as at the time of the supervision. We use the enrichment strategy for phosphoproteomic analysis here. The strategy itself is not critical, just know that you can enrich for phosphoproteins. Do this using any one of several approaches. This method here is called it's using titanium dioxide. It's immobilized metal affinity chromatography. And then we perform outlier analysis. We perform outlier analysis using a line that's derived from cutaneous T-cell lymphoma. We see the tyrosine kinase TYK2 show up as an outlier. Like I showed you for ABL, like I showed you for ALK in several iterations, which basically tells you that TYK2 is being driven by a process that makes it oncogenic in this context. So Thiru Belusami and Mark Keel in the lab did RNA sequencing and discovered that there was an NPM1 TYK2 fusion in the same line that showed the TYK2 outlier profile, which basically told us that TYK was being driven by this fusion kinase. And this was corroborated by a high read count in RNA-seq. So we prioritized NPM1 TYK2 based on the fact that TYK2 is an outlier kinase, we have read support for NPM1 TYK2, and the fact that it involved the tyrosine kinase is obviously attractive because those have very nicely therapeutically targeted. So Thiru cloned the breakpoint established that NPM TIC2 was a fusion genomically. We made fish probes using a break apart and a double fusion strategy. And when we tested these on clinical samples, what we observed was that 17% of the CD30 positive cutaneous lymphoproliferative disorders carried fusions involving TIC2. Importantly, some of the fusions were not NPM1, so TIC2 must be the target. The fusion preserved the C terminal of TIC2 and the N terminal of NPM1, just like it does with NPMF. So a little bit about TIC2. TIC2 is an intracellular JAK kinase. It's the original JAK kinase, despite the fact that it's known as TIC2. TIC2 actually means tyrosine kinase 2. But it was the original JAK kinase. But it didn't get a lot of attention because there was nothing wrong with it. Nobody found recurrent alterations associated with this disease. So its sister members, the JAKs, have a lot of attention because JAK2 is frequently mutated with some immunologic disorders, chronic myeloproliferative disorders that are not CML. JAK1 and JAK3 are known to be mutated frequently in T-cell invasion and other forms of cancer. Diru expressed the chimeric fusion, but before doing that, we did a Western blot that basically showed that the chimeric fusion was expressed only in the line that we detected the fusion, and that showed the high profile by phosphoproteomic analysis. Similarly, activation of phospho-TIC2 was observed exclusively in that line. Similarly, downstream signaling of STAT proteins, STATs 1, 3, and 5, was demonstrated using a conventional Western blot. Immunofluorescence microscopy showed activation of the STAT pathway in the samples or in the cell lines, that being MyLab 2000, that contained the fusion. When we looked at clinical samples using immunohistochemistry, we showed that phosphostat 5 was highly expressed and nuclear in the NPM1 TIC2 positive ALCLs. When we're topically expressed NPM1 TIC2 in HEC293 cells, basically we show activation of the STAT pathway, and when we express a kinase defective mutant of the fusion, those signals are all abolished, basically showing that the kinase activity we're seeing is dependent on the kinase activity, or the kinase activation of downstream pathway is dependent on the kinase signaling that's coming from TIC2. And this was corroborated by reporter assays. To demonstrate that this is indeed a targetable alteration, when we knock down using RNA silencing TIC2 in the line that carries NPM1 TIC2, we're able to retard cell growth in a significant fashion. So right about the time that we made the observation, a company that made a TIC2 inhibitor, and also there are commercial JAK inhibitors available, when we treated the samples using treated MyLab with the cell line that carried the fusion, using the inhibitor, we demonstrated nanomolar sensitivity to both JAK and TIC2 inhibitors, and we showed using the TIC2 selective inhibitor that the downstream signaling pathways of NPM1 TIC2 were also shut down. We showed specificity, so if you didn't carry the line that carried TIC2, the TIC2 fusion or activation was selectively inhibited in comparison to a line that didn't have the abnormality. Importantly, lines that also had JAK inhibition, JAK activation, were also inhibited, which basically says that TIC2 is sort of central and downstream to a lot of upstream kinase inhibition. And so here we're showing, again, nanomolar sensitivity. So this part of the presentation basically summarizes that there are recurrent TIC2 fusions in cutaneous T-cell lymphomas. NPM1 is one of the fusion partners. NPM1 TIC2 translocations result in constitutive activation of the TIC2 kinase. NPM1 TIC2 fusion protein exerts oncogenic effects through STAT activation. And TIC2 may be a novel therapeutic target in a subset of ALK-negative ALCLs. It's always good to make these observations and publish them, but like I tell all my trainees, it's more important that they are true. So, after this paper was published, Giorgio Ingrami, working from out of Cornell, also reported the observation of fusions involving TYK2 using other partners than NPM1. And if you recall, I said that although our founding member for this TYK2 fusions was NPM1, we knew there were other fusions because we did break apart probe fish in our initial search. Okay, so I will use the rest of my presentation to talk about another post-translation marker. So remember, we started talking about phosphorylation, specifically tyrosine phosphorylation as a mechanism of activation, downstream signaling, and oncogenic tyrosine kinase. So now I'm going to talk to you about a different kind of modification, and I'll use the example of ALK-negative ALCL to illustrate what you can learn from it. So N-glycoproteomics. So glycoproteins are excellent biomarkers. Glycosylation is a common post-translation modification. Glycoproteins are expressed on the surface of cells and they're secreted. In fact, they're the most abundant post-translation modification. And it's an opportunity for discovery biomarkers in lymphoma. So for those flow cytometrists in the audience, virtually all of your CD markers are N-glycoproteins. Virtually all of them. Okay. So the goal here is to use an unbiased approach to interrogate essentially all of the N-glycosylated proteins in the cell and see if you can learn about biology. So N-glycosylation occurs by a covalent bond between a sugar moiety and the nitrogen atom of asparagine. And there's other kinds of glycosylation, like O-glycosylation, which occurs in the hydroxyl groups of serines, threonines, but that's not what we're talking about today. In N-glycosylation, N-glycosylated proteins are destined for membrane localization. Okay? So it's one of the ways in which you can get the protein to go and sit in the membrane or secreted out of the cell. That's why all of the CD proteins are located on membranes. I told you, are very likely glycosylated. They're located on membranes. That makes them good therapeutic targets, against antibodies or even CARs. You can build CARs that recognize those N-glycosylated proteins. So the good news is that if you had a strategy to ask in an unbiased way, I want to know a protein that is expressed in this tumor that's not expressed in any other cell, then you can use that as a target for precision therapy, right? So the hypothesis was that we could use this to rationally select candidates as biomarkers and therapeutic targets in the form. So the strategy to do this is called solid phase extraction, or SPEG, as we like to call it, but the real thing here is based on decades of old chemistry. And so what happens is that you use one of several different approaches really to capture the N-glycosylated peptides. The strategy we use here is a hydrazide-based chemistry. And we take advantage of this enzyme peptide N-glycosylase F, which specifically cleaves the N-glycosylated proteins. That's at the asparagines. That cleavage leads to the conversion of the asparagines to aspartic acid. That conversion leads to a less than 1 Dalton change. That is less than the nominal molecular mass of a hydrogen atom. And that we pick up on acid. Okay? So what we're detecting is the deglycosylated peptide. Not the glycosylated, but not the sugar. We're detecting the deglycosylated peptide, which we know is deglycosylated because the asparagine has been converted into an aspartic acid. So all the biochemistry they teach you that most actually is important. However, else. So you use this approach, and we characterize a whole bunch of Delphine and a number of other people in the lab did a lot of work in characterizing the big number of human-derived cell lines. So 36, actually, numbers up to about 40. We also characterized a 6' lymphoma samples, and we did some validation and some functional validation. So N-glycosylated proteins are recognizable by a motif which is known as NXST. So N is the asparagine that ends up being glycosylated. X is any amino acid residue other than proline, and S or T is a serine or threonine that follows it. And when we look at the proteins that were identified as a result of our unbiased analysis, just under 60% of them have the NXT motif, just under 40% had NXS motif, and then we saw some alternative motifs, some of which have not really been associated with glycosylation, which is one of the things you gain from doing things in an unbiased way. We identified a number of novel glycosides in over 10% of the cases, and when we look through our cell lines, on average, per cell line, there's over 300, on average, in excess of 300 new glycosylated proteins. So compare that to what you might do by flow cytometry, which maybe you'll use, I don't know, 10 antibodies at the most. I'm telling you that for each one of these, we can interrogate with high mass accuracy and certainty 300 different proteins. Anyway, so let's validate our mass spec data. So using the universe of data collected from these 42 lines, we did hierarchical dendrograms. And hierarchical dendrograms, this heat map basically showed that all the B cell lines clustered together, all the myeloma lines clustered together, all the T cell lines clustered together, and obviously the B cell lines clustered differently from T cell lines. All the ALCLs amongst the T cell lines clustered together, and the NK's few lines that we had stayed together. And within the B cells, the mantle cell lymphoma derived cell lines clustered together with their own signature. The germinal cell derived B lines clustered together with their own signature, and so did the classical Hodgkin line that we observed. What this means is that there's intrinsic biology in the universe of data that we collect, right? Because this is unsupervised. You just ask the hierarchical dendrogram, the algorithm, to cluster based on all of the data you collected, and it's self-organized in this fashion. So the nice thing about mass spectrometry is that you can have quantitative data, right? For example, as a hematopathologist, I can take a look at a slide and I can say CD30 is weak. Okay? Dr. Taxa can look at the same place and basically say it's moderate. And Dr. Lim can look at it and say it's strong, and Carlos can look at it and say it's very strong. But there are no numbers associated with it. Okay? And so this leads to subjectivity, makes us actually miss stuff. So, for example, when I was a fellow, we used to be taught that classical Hodgkin disease did not express CD20. When I was a fellow, I don't know, a long time ago. But then you do antigen retrieval, better antibodies, and every now and then you see something that looks exactly like Hodgkin's disease or Hodgkin lymphoma histologically, and you see some, CD20 positive cells, and you say, the antibody is too sensitive. So blame the antibody. So the issue here is that we now have numerical ways to characterize the extent to which we can expect expression from any kind of protein. So here's the example. So CD10, the neutral endopeptidase, common acute leukemia antigen that we know is expressed in germinal center-derived neoplasms. The number we get for this line here is 36. Hodgkin didn't show us anything. ALCL didn't show us anything. And finally, the cellular B-cell lymphoma derived cell line showed us 9. So my expectation is someday somebody will do a study of primary mediastinal B-cell lymphomas and find out that some of them express weak levels or moderate levels of CD10. So here's the B-cell marker, CD19 exclusively expressed in the B-cell derived lines, CD22 exclusively B-cell derived lines, CD5 exclusively in the T-cell derived line, as you would expect, and so on and so forth, and get information on all of this. Okay, so especially if you're trying to publish this data, they usually expect you to be able to corroborate it with data from an orthogonal approach. So I'll show you that. So here's Western blot just looking at CD30. No expression in any of the B lines. High expression, so 28 and 32 ALCL. You all know that primary mediastinal B-cell lymphoma show weak reactivity for 30. And here's classical Hodgkin here showing reactivity, but obviously not as high as in ALCMs, which is what you would expect under normal circumstances, and we have numbers associated with that. So with this information in hand, we now took the clinical samples. Remember, I told you all of this data was generated from lines. The clinical samples, which we supplied, did end glycoproteomic profiling and supplied these to the mass spectrometrist and do the analysis and say, can you classify these without knowing what they are? And then by using this Pearson correlation plot, the very first set of samples of follicular lymphomas were accurately classified. The next set of, so the first set of samples were mantle cell lymphomas were accurately classified. Next set were follicular lymphomas. And this was blinded. I didn't tell them what the samples were. Just by the expression signature, they were classified appropriately using the N-glyco signatures, which was the first time that people who were mass spectrometrists in the lab actually believed that this works. So it's nice always to ask skeptical people in the lab. So using that approach, we wanted to know whether regulated we wanted to know what proteins were exclusively expressed in ALK-positive lymphomas. And to do this, we were going to interrogate the ALK regulome just looking at the N-glycoproteomics. And if we found out some things that were uniquely expressed in ALK-driven lymphomas, this would be therapeutic targets subsequently, and I'll show you what we did. So this study, when we integrated this with RNA sequencing, demonstrated to us that cytokine receptors, as you can see, the highest combination here, both IL-6 and IL-2 driven signaling here. Cytokine receptors are induced by ALK activity, ALK-positive ALCL. When we asked what proteins were uniquely expressed in ALK-positive lymphomas, we identified IL-2 receptor alpha CD25, which is an immuno which I spotted. It's available in your laboratory here. That's what the list of your antibodies, so you guys are doing well. And the other one is IL-31 receptor beta or oncostatin M. So you can see here, it only lights up in the ALCLs and not in the other forms, the B cell lines or the T cell lines. This is Western blotting analysis here, corroborating the data. None of the other lines show it. Only ALCL show reactivity for IL-2 receptor alpha. And when we looked at clinical cases using TMAs, even ALCLs that had translocations involving TPM3, sorry, these are not ALCLs. These are TPM3 positive ALCLs, also showed reactivity for IL-2 receptor alpha in 94% of the cases. With regard to IL-31 receptor beta, IL-31 receptor beta is also known as SMR. It is an IL-6 type cytokine receptor, and so that means that its ligand is IL-6 as well as OSM. Here you see exclusive expression in the ALK-positive ALCLs. Here's a positive control here. This is demonstrated by Western blots and also by FACS analysis. And in clinical cases, 100% of the ALK-positive ALCLs demonstrated reactivity for the cytokine receptor. So we wanted to know which one of these were vulnerabilities. For that, we used CRISPR-mediated genome vulnerability experiments and knocked out approximately 4,000 genes using 14,000 sgRNAs. And the way you're supposed to interpret these violin plots is the things that are located to the bottom of the violin plot are the biggest vulnerability. And this evaluation showed that the IL-6 STAT3 pathway is a big vulnerability, so is IL-2 STAT5, which is what we saw from the analysis we did with the integrated glycoproteomic analysis and transcriptomic analysis. So here's a list of some of the genes displayed here. So you remember that we said that IL-2 receptor alpha is selectively expressed in ALK-positive ALCL. So we wanted to take advantage of that for therapeutic purposes. And for that purpose, we used denileukin diptotox or ONTAC, which is a ligand associated with the diphtheria toxin. So the ligand, in this case being IL-2, ends up being recognized by the high affinity receptor, which internalizes the IL-2 into the cell, and this is carrying the diphtheria toxin, which kills the cell by terminating protein synthesis by toxin-mediated ADP ribosylation of elongation factor 2. So when you ask in cultured cells, ALCL cells, 3 different ones, get killed, whereas SOD-HL4, which doesn't express IL-2 receptor alpha, is unaffected. And this is by apoptosis, as you can see, using this luminescent assay and by PARP cleaving. Similarly, when we asked using IL-31 receptor beta, which you'll recall I said was selectively expressed in ALK-positive ALCLs, and we also know from transcriptomic analysis that IL receptor beta was also dependent on ALK activity mediated by STAT3. So if we inhibited STAT3, IL-31 receptor beta also went down in a time and dose-dependent fashion. If we silence IL-31 receptor beta using RNAi, we basically abolish the growth of colonies of ALCL cells. And when we xenografted these into mice, into immunodeficient mice, the tumor cells were dramatically reduced in size. So that was a strategy by which you can discover targetable proteins, which you can subject to inhibition and will have selective reactivity in the tumor cells. So to conclude, I just shown you that we've accumulated the largest compendium of N-glycoproteins in lymphoma, which includes almost 200 CD markers. The N-glycoprotein signatures accurately classify the lineage of the cell of origin, and many subtypes. It's nice to integrate N-glyco studies with transcriptomics, and from a mechanistic standpoint, uncovered the distinctive cytokine receptor JAK-STAT signaling network regulated by ALK-positive ALCL, an IL-2 receptor alpha, and IL-31 receptor beta are pathogenetically relevant vulnerability targets. So our overall conclusion here is that genomic and proteomic studies give you the opportunity to gain novel mechanistic insights into disease biology, helps you discover new biomarkers and novel targeted therapies in various human cancers. Generally, these are the people who do the work. I generally get the opportunity to talk about the work, but I don't do any work anymore. Of course, the brains of the operation, Dr. Lim, who you're going to hear from in a minute, the people who were involved in this study, formerly at the University of Michigan, Mark Keel, Thiru, Benki, who did a whole bunch of the mass spec. Of course, I mentioned Delphine Rowan, who did a lot of the glyco work, collaborators at the Broad, people who work with us, spent time in the lab. Dr. Chong, who's now back in Seoul. And generally, Carla, Leo Schwab, who actually started these studies and is now a pediatrician in Iowa. With that, I'm happy to take any questions. Thank you.